Well, one of the simple goals of object recognition is to write a computer program that will take as input a two-dimensional image or picture and identify or recognize the three-dimensional objects in the scene. Here in the computer science department at Rutgers, we're involved in numerous projects in object recognition, and in the next 15 minutes I thought I'd give you a sample of 3 or 4 of these problems. Specifically, what I'll talk about is, first of all, a problem which I call generic object recognition, which assumes that you have three-dimensional models of the world that you're trying to recognize in these two-dimensional images. Next, I'll talk about an alternative to that, where instead of representing the world as a three-dimensional object, you store a set of two-dimensional pictures or views from different viewpoints. That's called view-based recognition. The third problem I'll talk about is searching databases containing images, looking for similar images in a database to a query image. And the fourth problem I'll talk about is landmark recognition for robot navigation. Okay, if you were going to, say, design a home robot that would wander through your home and interact with the world, go fetch you a cup of coffee, for example, you need to build in a number of visual recognition behaviors to make this thing work. For example, you would want the robot to be able to go into a room and identify all the objects in the field of view. So in this case, it would come in and say, well, there's 2 coffee cups, there's a block, and there's this thing which might be a coffee cup or it might be a glass. We're not quite sure about that. The second thing you'd want to do is to be able to send the robot to retrieve or to find a particular target object, called target recognition. The third problem is if the robot actually has to go in and retrieve one of these objects, it's not sufficient just to identify it in the field of view. You actually have to recover some of the accurate shape and location of the object so you know where to put your robot arm to squeeze the thing. All right, that's the localization or shape recovery problem. As you're moving around, you may, the objects in the image are going to move, and you're going to need to track those objects. That's the tracking problem. And finally, if you're not sure what the object is, in this case, again, it's either a cup or a glass, you need to somehow intelligently move around the object to disambiguate the object, to find the missing handle on the other side to confirm that it's a cup, or lack of a handle would tell you that it's a glass. And finally, the one constraint is that for all of these problems, we're assuming that we only have coarse prototypical knowledge of the objects. So one model for a cup, for example, should suffice for all the coffee cups that are sitting in your cupboard. You buy this thing and pack it out of the box. It doesn't know the exact geometry of all the objects in your world. It has coarse prototypical knowledge of those objects. So what we've been working on are novel approaches to each of these problems. And one of the highlights of this work, I believe, is that we've been able to unify the solutions to each of these with a single object representation that assumes that three-dimensional objects are made up of three-dimensional volumetric parts. So I'd like to give you some examples of some progress that we've made. The first example is work with a number of institutions, including the University of Toronto, Aalborg University in Denmark, and the Royal Institute of Technology in Sweden. And what we're trying to do is develop a system by which you can hold up an object in front of a workstation camera, for example, and have it identify the object. The first step in the process is to take the raw original image that you see on the left and extract some kind of feature map. Process the image, give yourself some features to work with, and from these features then we're going to try to identify what the object is. We have a cup model which consists of a handle and a body, and the system is able to find part of the handle here and part of the body and confirm that this in fact is a coffee cup. Now, simply identifying the objects in the image, again, is not sufficient for recovering their shape for manipulation or localization. So the next videotape I'm going to show you now, I'm going to give you 2 examples. One where we're actually going to use the qualitative shape recovered from the image of this lamp to constrain model fitting processes that will recover an accurate three-dimensional model of the object. And the other simple example is going to show you as this object rotates in the image, or rotates in the world, it's going to move in the image, and what we're going to do is try to take one of these fitted three-dimensional models and track the moving object. So, let me turn this off. Charles, you can let it run. Okay, so here's the lamp. What we're going to do now is use qualitative knowledge about the shape of the parts that we've recovered to fit three-dimensional models to these parts. And this is running real time on a workstation. So we do it part by part, and we don't need to constrain the initialization of the parts. We start them all in some position in the world, and they immediately move to the part that they're trying to fit, and they use the relevant pieces of the contours to recover the shape of the model. Now, from a single two-dimensional view, we can't solve for the actual depth. We need two views or stereo information to recover the true depth of the parts. So we can apply the same procedure by simultaneously fitting object models to the left view and the right view in a stereo pair, and then we can actually fuse these views together. So if we have left and right images of a highlighted object in the scene, then we're going to fit a model to this view, we're going to fit a model to that view, and then we're going to finally fuse the two models together to recover its true position and scale in the world. This is work in collaboration with the University of Pennsylvania. We've taken the same process and applied it to three-dimensional images. We're giving an explicit depth of a point or pixel in the world. And this is work with the Media Lab as well as the University of Pennsylvania. So simple objects taken from a Michigan State database, extracting the qualitative shape, and then using that shape to constrain fitting processes that would fit the two parts of this object. That's the first part. And then the second part, using these partial contours, will fit the second piece, and we can actually rotate. These are three-dimensional contours now. Since we have 3D data, we can rotate that and see the actual fitting proceed on the second part here. The final thing I wanted to show you on the tape is the tracking process. So once we've recovered one of these models, then we have a sequence of these two-dimensional images. And if we recover the edges from these images and blur them, that you see in this white blurry region here, then we get a sequence of these blurred images. You can think of this blurred region here as a field of attraction or a force field which is going to tug on these points on the model projected into the image. And that will become clear when we actually start pulling the model. So you can think of this blurred white here, for those Trekkies in the audience, as some kind of tractor beam which is going to try to pull this object into the white area. As long as the nodes of the object fall in the white area, they're going to be attracted and pulled into a local minimum. If you pull them too far out of the white area, then there's no force of attraction exerted on the model, and it's going to float around in space, as we see in this example. Pull it back. Still too far. Pull a little closer, and there it comes. Okay, we can stop the tape. Okay, well, the problem with three-dimensional models is their appearance changes depending on viewpoint. So in fact, it's very difficult to try to recognize or identify a three-dimensional model in a 2D image. One alternative is to take the three-dimensional object and take a zillion pictures around the object and store all these pictures so that when you see a two-dimensional view of the object, you know it must match one of this huge database of pictures that you have. So that's one of the problems that we're looking at. And therefore, recognition then is taking a picture of an object and finding the closest view in the database. So what we need then is a description, a compact description of a given image that doesn't change much with small changes in viewpoint of the object, and also doesn't change much as the object is scaled in the image, or translated, or rotated in the image plane, or even rotated in depth. This is joint work with Elon Marsick of the Cape Center and my student Ali Shukapande in the Computer Science Department. So what we've come up with is a description of an image which captures image features at some appropriate level of abstraction. So in fact, this map, where you see these circles here, is mapped to this graph or tree mechanism, where the larger features, for example, the head, exist at higher levels of abstraction in the graph, and the smaller features, these portions of the ear and so forth, exist at the lower levels of the tree. So what you want to do now is for each of your images of the object, you have a tree in the database. You pull out a tree from your test image, and you want to find the closest tree, the closest graph in the database. What we've developed are graph distance measures that will take two graphs and compute their similarity or distance. For an example of this system in action, we have a database of some 1,400 views. Here's one of the objects, a piggy bank, and here are three adjacent views. Here's a middle view, here's moving the piggy bank to the right a little bit, and here's moving the piggy bank to the left a little bit. And here are two views of two other objects in the database. What you see here are the computed distance between the piggy bank and these other views. And of course, the two other views of the piggy bank are much similar than the view of the coffee cup and the lamp socket there. So this is work in view-based recognition that we're doing. Now, the third problem that I wanted to look at is image database search. You've all noticed the proliferation of images on the World Wide Web, photo CDs and so forth. Well, wouldn't it be nice if you could take a picture, and instead of having to type in keywords for the image, say, get me all the pictures that look similar to this one. All right? And we're looking at an application in dental radiographic image database search, and this involves a number of people across campus, in addition to one person at Boston University. So let me explain what the problem is. There's a database of patient records, and for each patient record, there's a series of digitized x-rays that are tagged to that record. And what happens is, every time there's a lesion identified by a radiologist in one of the x-rays, that radiologist fills out this diagnostic form, which describes the actual lesion, its shape, its radiodensity, its color, and so forth. And this gets saved into the database. So what happens now, the next time the radiologist gets one of these lesions, wouldn't it be nice if they could circle the lesion and say, show me the diagnoses of all the similarly shaped lesions in the database. And let me use that information to help me diagnose the current one that I'm looking at. So with a tool then, developed by Ivan Marstik at Cape, we can outline a particular lesion, and then we can search on that in our database. And what we get are the best four examples. 1, 2, 3, 4. These are various outlined lesions from other patient records in the database. And then, this is all a web interface, by the way. Now what the radiologist can do then is simply click on one of these images. And what they finally see then is a diagnosis for the similarly shaped lesion in the database. And then you can take this information and use it to help you fill out the diagnostic form for the current lesion. Finally, the last problem that I wanted to show you is visual navigation, also a recognition problem. This is an image of an industrial bay in a nuclear reactor operated by Ontario Hydro in Toronto. People we're working with on this problem. Also people in the University of Toronto and two Israeli institutions, the Technion and the Weizmann Institute. What you want to do is have the robot navigate this environment by looking at landmarks, recognizing a landmark and saying, I know where this is, etc., in order to localize its position in the world. Now, what is a useful landmark? A useful landmark is obviously something that's widely visible. It's not something that's hidden behind a desk here because you can only see it in a very small range of viewpoints. It's also something that's very unique, all right? A simple light bulb, since there's many light bulbs in the ceiling, is not very unique. So you'd be confused as to where you are if you just look for light bulbs. So there's a number of ways of solving this problem. One is you can put up your own landmarks on the environment. For example, you could put big purple spots on the wall, one purple spot, one pink spot, and if this robot could detect color quickly, it would know where it is. But this is cheating. All right? The next thing we could do is try to hold the robot's hand and walk it through the environment, and when we saw something that we thought was an interesting landmark, we could point the camera and say, remember the image of this. Remember this from now on as this particular useful landmark. That's getting better. But what we want to do is have the robot autonomously roam around this environment and to come back and say, these are the optimal set of landmarks. Having looked at the world, having looked at the uniqueness of all the things in my environment, these are the things that I choose to navigate by in the end. And that's what we're working on. And just very briefly, to give you an idea of what this problem is, consider this a floor map of an environment here in black. There's some obstacle here. And these crosshairs here, these are these are landmarks. These are things that the robot can detect in an image. So what we want to do is choose some subset of these landmarks, all right, such that the contiguous regions that can see these landmarks is minimal in number and maximal in size. All right, so for example, all the points in this tan region here can see this landmark. All the points in this green region can see this landmark. This thing is kind of left out from both that one and that one, so it needs some landmark if you're in here. And so we want to basically color this world in terms of a minimal number of regions and a minimal number of landmarks. That's the kind of problem that we're trying to solve. And once we have that then, once the robot is actually driving through one of these regions, it can fix its camera on the landmark and track that. And when it crosses the boundary into another region, it has to go through a fairly expensive process to stop tracking one landmark and start tracking another landmark. So let me conclude by saying that in addition to these recognition problems, we're also looking at, through the Cognitive Science Center, we're studying human object representation and human object recognition. It's my sincere belief that a better understanding of the human visual system will lead us to the design of better computer vision systems.